Welcome back to the deep dive. So I want you to start today by just looking at that machine in front of you.
Your laptop, your desktop.
Exactly.
Sure.
Whether it's a sleek laptop or, desktop tower humming away, we tend to think of it as a tool for checking email.
Or keeping way too many browser tabs open.
Guilty. Or maybe streaming a movie. But I want to propose a different idea. Inside that metal case, specifically inside the part that handles your graphics, there's a dormant supercomputer. And for most people, it's just sleeping on the job.
That is a really fair assessment. I mean, for decades, the graphics processing unit, the GPU, it was a specialist.
Right.
Its only job was to draw pictures, render explosions in games, smooth out lines in a CAD drawing, that kind of thing. But in the last, 15 years, a huge shift happened. We basically figured out how to trick this hardware, which was designed for pixels, into crunching raw numbers for science.
And that is our mission today. We are exploring general-purpose GPU programming. We're going to figure out how we went from just rendering video games to simulating black holes and powering this whole AI revolution.
And how you can actually do it.
Yes, and more importantly, how you can actually access this power without needing like a PhD on computer engineering.
It really is simpler than people think. It's just about understanding that the same architecture that makes light reflect realistically off a virtual car, that same architecture is also incredibly good at predicting the stock market or, diagnosing a disease.
Okay, let's unpack this immediately. Because on the surface, a chip is a chip. My computer has a CPU, right? The central processing unit. That's the brain.
The brain?
Yes. Why isn't that enough? Why do we need this separate graphics card to do math?
It all comes down to a fundamental difference in philosophy. Latency versus throughput.
Okay.
Your CPU is designed for low latency. I think of it like a master craftsman. A modern CPU might have, say, 8 or 16 cores.
And these cores are smart.
They're geniuses. They can switch tasks instantly. Write an email, play music, run the OS, check a spreadsheet. They're built to finish one complex task as fast as humanly possible.
So the CPU is the ultimate multitasker. It's flexible, it's quick on its feet.
But it has a limit. I mean, imagine you ask that master craftsman to move a giant pile of sand, but one single grain at a time.
Oh, that would take forever.
He could do it, but he's going to be expensive and slow because he's overqualified. Now, look at the GPU.
Yeah.
The GPU isn't a craftsman, it's an army of ants. It has thousands of cores, tiny, simple, relatively dumb cores compared to a CPU core.
Thousands.
But they are designed to do one thing and one thing only: parallel work.
Parallel work, meaning they all do the exact same job at the exact same time.
Exactly. In a video game, you might have 2 million pixels on the screen. You need to calculate the color for every single one of them 60 times a second. The math for the pixel up here is basically the same as the math for the pixel down there.
So you need a genius for that.
You need sheer volume. You need throughput.
I love that army of ants analogy. So if I give the CPU a complex logic puzzle, it wins. But if I say multiply these 10 million numbers by 2, the CPU just chokes.
The CPU would do it one by one very fast. The GPU does all 10 million at the exact same instant.
The GPU crushes it.
And that was the aha moment scientists had around, 2006. They realized that physics simulations, weather forecasting, and eventually deep learning, they aren't logic puzzles.
They're massive piles of sand.
They're massive piles of sand. There are millions of tiny math problems that can all be solved at the same time.
Okay, so we have this army available. But here's the problem. I don't speak ant. I speak English or, maybe Python if I'm feeling ambitious.
Right.
How do we actually give orders to this army? This feels like where the real barrier to entry usually is.
It used to be a massive barrier. I mean, you practically had to be a hardware engineer. But now we have these things called APIs, languages, and frameworks that act as translators.
So you speak to the API.
And the API screams at the ants for you.
Okay, let's break these down because I see a few acronyms tossed around all the time. The big one, it seems, is CUDA.
CUDA is the heavyweight champion, no question. It was created by NVIDIA, and it's the main reason they dominate the AI space today. It stands for Compute Unified Device Architecture.
And if you're serious about this stuff...
If you are doing serious scientific computing, you are probably using CUDA. It gives you incredible fine-grained control over every single aspect of the card.
But there's a catch, isn't there? It's a walled garden.
It is a very nice, very powerful walled garden, but yes. CUD only works on NVIDIA cards. If you have an AMD card or an Intel chip, CUD won't help you at all.
And it's not easy to learn?
Well, it's based on C++ May, so it has a moderate learning curve. You have to manage memory manually, allocate your own resources. It's not for the faint of heart.
Okay, so if I'm an AMD user, or I just don't like walled gardens, what's my alternative?
Then you look at OpenCL. This is the open computing language. It's a standard managed by a whole group, a consortium, not a single company.
So the idea is?
The philosophy is write once, run anywhere. You write your code, and theoretically it runs on an NVIDIA card, an AMD card, an Intel processor, even a mobile chip.
That sounds ideal. Why isn't everyone just using that?
Because being a diplomat is hard work. To make code that runs on literally everything, OpenCL requires a lot of what we call boilerplate.
Boilerplate.
You have to write pages of setup code just to get ready to do the actual math. It's verbose, it's often slower to develop in than CE, even if the end result can run on more hardware.
I see. So CA is the sleek proprietary sports car, and OpenCL is kind of the reliable but clunky public bus.
That's a pretty good way to put it.
What about the hard mode I keep hearing about? Vulkan.
Vulkan is interesting. It's the successor to OpenGL. It's a modern, very low-level API that works on almost everything: Windows, Linux, Android. It is incredibly powerful, but it strips away all the safety rails. The driver doesn't hold your hand at all. You have to manage the memory, the synchronization, everything.
So if you mess up, you could,
You might crash the whole system.
Yeah.
It's fantastic for game engines where every millisecond counts, but for a researcher just wanting to multiply matrices, it's way overkill. Too steep a hill to climb.
And on the flip side, we have the web. I saw web GPU on our list.
That's the newcomer. The idea is to let you access the GPU directly through a web browser just using JavaScript.
No installation.
No installation required. It's still evolving, but the promise is huge. Imagine running a complex physics sim or a high-end 3D model right in Chrome.
Okay, so we've got the heavy-duty C-style languages, but let's be real. Most people listening aren't looking to write C++. They just want to solve a problem. Is there a way to use this power without getting bogged down in all that memory management stuff?
Absolutely. And this is where the ecosystem has matured just beautifully. We now have high-level frameworks, mostly in Python, that handle all that translation for you.
This is the easy button.
This is essentially the easy button. If you look at PyTorch or TensorFlow, which are the standard tools for AI, they let you write normal, readable Python code. You define your data, you define your math, and when you hit run, the library talks to CUDA or Metal for you in the background. It moves the data to the GPU, does the math, and brings the answer back.
So I don't even need to know how the GPU allocates memory. I just need to tell PyTorch, hey, put this on the GPU.
You literally type .to CUDA, and it happens. It abstracts away all the pain.
Wow.
And for people who aren't even doing AI, maybe just heavy math, there's a tool called Numba.
I was so skeptical when I read about Numba. It claims you could just add a decorator, like a little tag, to your Python function, and it magically runs to the GPU. Is it really that simple?
It's not a gimmick, but it does have some rules. You add a tag, like @CUDA.jit. Numba then looks at that specific function, translates it into machine code for the GPU, and runs it.
What's the catch?
The catch is the function has to be compilable. You can't use dynamic Python features. You can't have print statements inside it. It has to be pure math. But if it is, you can see speedups of 100 times or more with literally one line of code.
Yeah. That is just wild. It sounds like we've moved from hardware engineering to software Lego blocks.
That's a perfect analogy.
So speaking of Lego blocks, I want to talk about the tools. We aren't just writing raw code. We're using libraries. But instead of just listing them, let's look at how they're actually used. The source material gave some great real-world examples.
Let's do it. Context makes the tools make sense.
Okay, start with the most famous one. Self-driving cars. We all know they use GPUs, but what is actually happening inside that car's brain?
This is a perfect example to explain the difference between training and inference.
Okay.
Before the car ever hits the road, it has to learn what a pedestrian looks like. That's training. It takes weeks of crunching millions of images on huge server farms, usually using PyTorch. It's the heavy lifting.
So the car has learned, now it's driving down the street.
Now it needs inference. It sees a shape. It needs to decide instantly, is that a person or a mailbox?
No time to think.
It can't take 3 seconds to think about it. And this is where a specific library called TensorRT comes in. TensorRT.
It's an optimizer. You take that big, heavy brain you trained in PyTorch and you run it through TensorRT. It basically strips out all the parts needed for learning and leaves only the parts needed for deciding. It fuses operations together to make them lightning fast.
Ah, so the car can process the image and hit the brakes in milliseconds.
Exactly. It's like slimming down for a race. You shed all the weight you don't need.
What about something completely different? Medical imaging. The notes mention MRI scans.
This is fascinating because it's not AI. It's pure, hard math. An MRI machine doesn't take a photograph. It records magnetic signals, just raw, messy waves.
Okay.
To turn those waves into a picture of your brain, you have to use a mathematical operation called a fast Fourier transform, or FFT.
I've heard of FFTs. It's like unmixing a smoothie back into its original ingredients, right?
That's a great analogy, actually. It breaks a complex signal back into simple waves. But to do that for a high-res 3D scan requires billions of calculations. If you do that on a CPU, the doctor is waiting 20 minutes for the image to show up. And nobody wants to wait 20 minutes when they think they might have a tumor.
Precisely. So developers use a library called CUFFT. It's part of the CUDA toolkit. It's a pre-built Lego block specifically for this math. They drop it into their code, and suddenly the GPU crunches those waves in seconds.
Wow.
It allows for real-time 3D rendering of the body during surgery.
That's incredible. It's literally saving lives by doing math faster. Okay, one more that I think fits our audience well. Data science. A lot of people use Python and pandas for data analysis.
Right. And anyone who uses pandas knows the pain of that loading bar. If you have a CSV file with, say, 200 million rows of retail data,
Your computer just freezes.
it runs on the CPU, it's single-threaded, it's slow, you're sitting there sipping coffee. The solution here is a library called Rapids.
Rapids.
And Rapids is brilliant because it mirrors the pandas syntax. You can take your existing code, change import pandas to import cuff, and suddenly that 200 million row data set is loaded into the GPU's memory.
Wait, really?
Operations that took minutes now take milliseconds because all those thousands of cores are sorting the rows at the same time.
That seems like the biggest productivity hack ever for business analysts. You don't have to learn C++. You just swap the engine.
It really is. It turns a workstation into a data supercomputer, effectively.
Now, I have to play devil's advocate. We've talked about all this power, but we haven't talked about the price tag. I mean, a few years ago, during the crypto boom, you had to sell a kidney to buy a high-end GPU.
Oh, yeah.
Do I need a $3,000 card to get started with this?
I'm very happy to report that the crypto tax is mostly gone, but the answer is a definitive no. You do not need a top-tier card.
Okay.
If you are learning, you don't need raw speed. You just need functionality. A mid-range card from 4 years ago, like a GTX 1660 or a Radeon RX 5600, is perfectly capable.
So what's the bottleneck then? If I go cheap, what am I losing?
You're losing VRAM, video RAM. That's the dedicated memory on the card itself. The GPU is the army of ants, but they have a very small desk. They can't hold a lot of data at once. If you want to train a massive AI model, you need, 24 gigs or 40 gigs of VRAM. But for learning, for running your first few neural nets, 6 or 8 gigs is plenty.
What about the laptop crowd? I see gaming laptops are huge, but can I do this on like a MacBook?
You can. Apple has gone their own way with Apple Silicon, the M1, M2, and 3 chips. They have what's called a unified memory architecture.
The GPU shares memory with the CPU.
Exactly. And it's surprisingly good for AI. You just use the metal backend in PyTorch. It just works. It's not as fast as a giant server card, but for development, it's fantastic.
And for the person listening who has a Chromebook or like a 10-year-old ThinkPad, are they just left out?
Not at all. In fact, they might have an easier time than someone building a new PC.
Oh?
You can use the cloud, Google Colab, Cattle Kernels, Amazon SageMaker Studio Lab. These are free services. You open a browser, you get a notebook, and on the back end, Google or Amazon just assigns you a slice of a powerful GPU.
So I'm typing on my $200 Chromebook, but the code is actually running on a $10,000 NVIDIA card somewhere in a data center.
And it costs you $0. It's the ultimate democratization of this tech. The barrier to entry isn't hardware anymore. It's just curiosity.
Okay, you've convinced me. I want to wake up my supercomputer. What is the actual workflow? If I sit down tonight to do this, what are the steps?
Step 1. The foundation. Make sure your graphics drivers are up to date. This sounds so boring, I know.
Have you turned it off and on again of GPU programming?
It really is. But if your drivers are old, the software literally won't see the hardware.
Got it. Step 1, drivers.
Step 2, choose your weapon. I strongly recommend Python. It has the best community, the best tools. Install Python and then install PyTorch. The command is usually just pip install torch.
And how do I know if I succeeded? Is there a hello world equivalent?
There is. In PyTorch, you open a terminal and type 2 lines, you import torch, and then you print torch.cuda.i is available.
And if it says true?
If it says true, you're in. You have control, the bridge is built.
And if it says false?
Then welcome to the community. You're going to spend some time on Stack Overflow or Discord. But that's part of the process. Debugging environment issues is like a rite of passage for everyone.
That's a good point. You aren't doing this alone. There are thousands of other people figuring out why their tensors aren't matching up.
And the documentation is so much better than it used to be. The path is well trodden now.
We've covered a lot of ground here. We've gone from the army of ants architecture to the languages, the easy button of Python, and the real-world tools that are reshaping entire industries.
It's a complete transformation of what personal computing even means. We used to measure computers by how fast they could open a word processor.
Right.
Now we have personal devices capable of training neural networks that can paint or write code or simulate physics.
It's just wild to think that the same tech that was invented to make water look realistic in the video game crisis is now being used to fold proteins and cure diseases.
It's the law of unintended consequences, but in the best possible way.
I want to leave the listener with a thought. We often talk about supercomputing as this thing that happens in government labs behind blast doors. But if you have a GPU, you have that parallel processing power sitting in your lap right now.
The hardware is no longer the bottleneck. It's not the excuse.
Exactly. So the question isn't, can I run the code? The question is, what do I want to solve? If you could crunch millions of calculations a second, what problem would you attack? Would you map the stars? Would you analyze your own spending habits? Or would you try to build an AI that writes better podcast scripts than we do?
I hope not too much better.
Fair point. We need to keep our jobs. Thanks for joining us on this deep dive. Go wake up that supercomputer.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.